Welcome, Math Fancy, to Lesson 2, 4.2, Relationships between two quantities. So we're talking about linear relations, and what they're talking about is basically the comparison of two sets of elements, and elements we're talking about x and y variables. So we're talking about different ways we can actually describe those. So if we take a look here, we've got a list, and a list tells us exactly how many different ways we can represent a comparison between two different quantities. So we could describe it in words. We could say, I don't know, it costs this much money to purchase this amount of something. Okay, comparing money to amount. We could also use a table of values. Here's our table of values right here. Whenever we're dealing with tables of values, they do use different letters. The reason they do so is so that they can describe the problem-solving situation we're talking about. If we talk about this one right here, the S is representing X, and the C is representing Y. So, that is the representation. We're considering this equation here, and we're looking at exactly different ways we can represent that information. So, the mapping diagram is the next way we're talking about. The mapping diagram are these two circles below. Now, they basically are another table of values, and it's a different way to represent a table of values, because they're not exactly going across in a row with each digit. What they do is they list them chronologically, which means they're in proper order, least to greatest, or greatest to least, depending on which way they've done it. In this case, they're going least to greatest. Now what they've done is they've drawn arrows or spokes from each number. And that representation is that each number would be a coordinate pair. So the one I've drawn in red would be 20, 10, and that would be its coordinate pair. Again, for x and for y. So we've taken a look at mapping diagrams. The next thing we can take a look at is the actual equation. Here is the equation we're talking about. Now we know from previous units that when we have something with exponent 2, with our exponent laws, we have a descending order here. We've got exponent 2, we've got exponent 1, then we've got a constant. Well, our constant is always our y-intercept. That's where it tells us where it touches the y-axis. So if I look along this y-axis, this number here, 12.4, is where it's actually going to be touching the y-axis, which would be approximately way the heck up there. So, again, back to my equation. Each of those quantities of values there are describing something different about our graph. It's just another representation again, and we're going to describe how to create equations from tables of values shortly. Then we can talk about ordered pairs. So we have a set of ordered pairs here, and ordered pairs will be the exact same thing that I just wrote here, and an ordered pair is basically taking something out of a table of values and writing it with commas and brackets around it. That again is a location on a grid. Your location again, this would be x, this would be y. So again, x alphabetically comes before y, and as you read a table of values or anything, you always start on the left and go to the right. As we do so, x would come first in a table of values, y would always come second. And that's how we read actual coordinate pairs as well, these ordered pairs. X is always first, y is always second. The last thing we can take a look at, the last couple, are graphs and function notation. Now, graphs are this, we have a situation right here. So here's one graph. That should go straight there. So we have one graph right here. That's describing the equation that we have right here. And each of those coordinate pairs. Each of these was graphed on this set of Cartesian plane. Function notation, all that means is they change x and y to a different letter. So in this case, x they changed to s and y they changed to c. That's function notation. They changed up the x and y letters to represent the problem-solving situation that we're dealing with. Let's take a look at the next slide. So, when we talk about the previous example that you have on the top of your page, we talk about the two variables, and again, it had c and s. Again, c was y and s is x. So, if a situation is talking about cost and speed, cost depends on the speed in this example that we're talking about. So, Because the cost is dependent on the speed, that means it is called the dependent variable. Now the dependent variable is also called the output. Okay, it's dependent and it's the output. You input an x, x does something and it changes what y becomes. So that gets us right into what our x variable is. Our x variable is our independent variable, so s would be the independent variable over here, who is x, and it's also called the input. And we can remember those in a couple different ways. The letter IN for independent in this list here starts with the letter IN, and so does the word input. That also starts with the letter IN. So you can remember that if you have to, that the two words that belong with the x variable are independent and input. Now, y is always the dependent variable. X is the boss, and he bosses y around. He makes y change according to what x decides to do. So in this case, x was multiplying by 3 and then subtracted 5. So the answer of y is going to change according to what x numbers we input to this equation. It's substituting for x. So for example, if I go 3 times 1 subtract 5, I'm going to get a y value. Again, that's my x. I'm going to get a y value after I do BEDMAS and multiply, then subtract 3 times. Subtracting 5 gives me a -2. I do that same process, 3 timesing by a different x value, subtracting 5. So if I choose a different x value, the first one I chose a 1, this time maybe I'll try a 4. If I put a different number in, as you're going to see, it's going to change what the y number becomes. 3 times 4 is 12, subtracting 5 gives us a 7. So because the y numbers are different, they changed according to what the x variables did and what they changed to. So again, y depends on the change of what x tells it to do. Alrighty. The domain and range, that's our next topic. Domain and range talk about the different parts of our graphing. So the domain talks about all the possible inputs. How many different x numbers could I input to these? Okay, that's what the domain is talking about. The range would be what boundaries would I end up with for a y. So what boundaries would I end up here for the y values? Okay, that's what the domain and range is talking about. And we'll talk about that in more detail in a couple lessons later. Okay, I'll get you to take a look at that now. Make sure you've got everything highlighted as you should. We're going to move on to the next question. So we've got a new equation. They're giving us the equation y equals 2x minus 5, and it wants us to input different numbers for x so that we can find out what numbers we're going to get for y. So again, I check and see how many different numbers I have for the x. I've got 1, 2, 3, 4, 5 different numbers for x, which means I'm going to have to write this equation 5 different times. So I'm going to do it this way. 2 timesing by a different number as x, subtracting 5 will give me a y number. 2 timesing by a number, subtracting 5 equals 2 times a number, subtracting 5 equals 2 times a number, subtracting 5 equals, and our last one, 2 subtracting a number equals 5. Subtract 2 times a number, subtracting 5 equals of y value. So let's take a look. We have the input -2. -2 is going to go to our first one. Then we've got our -1. It's going to go next. And so on. So the 0, +1, +2. Now again, like we did before, we're going to do BEDMAS and solve the multiplying part first. So I'm going to take 2 times -2 to give me a -4. So I've got a -4 subtracting 5 to give me a -9 for my y value. So now the -9 I know matches with my -2. So I go over to my chart and now I write the -9 in. Just erase the arrows here so you can see where I'm going to put the -9. So the -9 matches up with my 2. Okay, that's the digit I used in my substitution. Next I'm going to be using the 1. So what number will it create for y? Let's take a look. So again, I've got 2 times by negative 1 to give me a negative 2. Negative 2 subtracting 5 is going to give me a negative 7. So I go over to my chart and I write a negative 7. The next digit. 2 times 0 is 0. Anything times 0 is 0. We subtract 5, we get a negative 5. So 0 subtracting 5 does give us a negative 5. Again, I go to my chart, my table of values, and I write in my new value of y. As you can see, every number I change for x, I get a different number for y. Alright, let's take a look at the next one. 2 times by 1 gives us a positive 2. Subtract 5 gives us a negative 3. Hopefully you can see a pattern showing up here. This one's going to give us a negative 3. So this one's going down by 2, which means it's actually plusing 2. We're getting close to 0 as a negative number. If you get closer to 0, you're actually adding a digit. So these guys are adding 2 every time. So if I added positive 2 to 3, positive 2, I would get a negative 1. So that's what this should give me. Let's go back and check and make sure. Here's my pattern. 2 times 2 is 4. Subtract the 5. Yes, I do get negative 1. Now we're going to write the ordered pair that results. So again, remember, this is a location on our Cartesian plane. So we're going to have negative 2, comma, negative 9. This one becomes negative 1, comma, negative 7. Oops, pardon me. That one didn't turn out so good. The next one comes 0 and negative 5. Remember, we must put brackets around. If it's an ordered pair, it does belong in brackets. 1, negative 3, and 2, negative 1. There's our ordered pair. Now we're actually going to go to the page next to, actually should be below in your notes, and we're going to actually graph those digits. So let's graph those digits on the next page, please. So we've got negative 2, negative 9 is our first one. So I'm going to go 2 left to negative 2 and down to negative 9. There's my first dot. That's how you find out where you put your dot. Okay, I'll just erase my trail there. So our first dot is at negative 2 and negative 9. Let's take a look at the next one. We've got negative 1, negative 7. So now we're going to go to negative 1, go down to negative 7, and make our next dot. And again, I'll just erase my little trail for you. Hopefully we're seeing a pattern. You see a pattern here, we're going to go right 1 and up 2. So if I continue, I'm going to go right 1, up 2. And my next coordinate, if we take a look, is actually 0 and negative 5. So again, back to my graph, I take a look. And what number did this guy end up at? He ended up at our 0, negative 5. 0 for x because he didn't go left or right from 0. Here's our 0 right in the middle, our origin. That number did not go left or right. He stayed at 0 and he went straight down. All right, our next number in our ordered pair list is 1 and negative 3. So now we're going to go over and go to 1 and then go down to negative 3. There's our next one. And the last one we have is 2 and negative 1. So now I go over to positive 2 and go down to negative 1. Now I've created the dots that create my linear relation. So it says plot the ordered pairs. We just did so. Connect our points on the grid and extend the line in both directions with arrows at both ends. So that one's telling me right here that I'm going to join my points and they will continue in that direction infinitely. So the one thing that we have to remember though, as they told us, we need to put arrows on everything. So I'm going to put an arrow here and an arrow here. Sometimes though in your booklets and sometimes on quizzes and tests, the program we use to create those questions does not allow to put arrows on the end of your lines. So if you notice some questions that don't have arrows, you might think those lines actually end. They don't. The ones that we deal with that will end, you will see them specifically something similar to this, where you know that you can see a start point and you can see an end point. Okay? Or it's within the boundary of the graph and doesn't extend past. For example, I could have one doing this, doesn't extend past my boundary, so I know it starts here and stops here. Otherwise, if they go right to the edge of your boundary, we know they should automatically have an arrow on both ends. Let's put our arrow right up here, extending past our graph. Okay, now it says use the equation to determine the value of y when x is positive 6. X being positive 6. My equation is y equals 2x subtract 5. So now I'm going to substitute. It says put x is 6. So now I'm going to put a 6 where x is. That's going to give me my new y number. So I've got 2 times 6 subtracting 5. Doing my BEDMAS, that's going to give me 12. Subtract 5, y is going to be 7. Now I can plot that point. Go to positive 6 and y is 7. So as a coordinate point, it would be this. 6, 7. I go over to positive 6 and go up to positive 7. Let's see here. 7, 6, and 7. So my graph is off a little bit from what I've drawn. I need to just move my boundary here a little bit. That's where it should be going. Okay, so yes, it's going to cover where it should. So, as we can see, the point we just found is on the line. Okay, this point right here did end up on our line. Now it says, if we say use the graph to determine x when y is 3. Now using our graph, the one that we have written here, not those little blue ones, using this graph here, it says when y is 3. So you know a y number. What you do is you start at 0, go up to positive 3 on the y. So it's a y number, you're looking for x, you go to the right to hit the line. The minute you touch the line, you go straight down and find out what x number that would have been. And that number is going to be a 4. So we know that x is 4 when y is 3. As a point, that would be 4, 3. All right, let's take a look at the very last blank it's telling us. It says the relation is called a blank relation because the graph is a straight line. Well, those are the ones we call linear. Okay, and we can add one more thing to the bottom. It's also a linear. Because the largest exponent on the x variable is a hidden 1. Okay, so in linear equations, we had, in this example, we had y equals 2x subtract 5. Look at my x. X determines the type of graph I'm going to have. He is x exponent 1. That 1 tells us he's going to be linear. Okay, this concludes lesson 4.2 of relationships between variables for Unit 4.